Welcome everybody to our webinar today. I do see that we've got a few people that are still trying to log on, so if you will be patient with us, we will get the webinar started in just about 1 minute. Thank you. Okay, we'll go ahead and get started here. Welcome everybody to our webinar today. My name is Jill Browning, and I'll be the moderator for today's webinar on sulfate removal from mine water. Before we get into our presentation, I just wanted to let you guys know that you should be hearing me now, as the slide says, and that there are two different options for audio. You can log in using either your computer or via your phone, so either of those options should work for you should you have any issues arise throughout the presentation. And then lastly, if you would like to ask questions throughout the webinar, please feel free to do so at any time. And then at the end of today's presentation, we do have some time set aside for a question and answer session. So feel free to ask any questions that may come to mind, and we will try to get to as many questions as possible at the end of today's presentation. And then one final thing to note on there, to ask questions, you can ask on the questions panel that is on the right side of your screen. And now I'd like to introduce our speaker for today's presentation. Sri Munisani is a process engineer for Veolia Water Technologies and has worked for Veolia for more than 11 years. Sri's expertise includes physical, chemical, and biological treatment of water and wastewater. His industrial experience is in metals, mining, and oil and gas. Sri holds a master's degree in environmental engineering and a BS in chemical engineering, and is also a licensed professional engineer. And now I'd like to turn over to Sri.
Thank you everyone for joining, and thank you Jill for introducing me. The content of the presentation includes, I'm going to start on the sulfates limits in the mining industry globally. Then I'm going to talk about the major sulfates technologies that are currently available. And I'm going to talk about the two-stage sulfate process, sulfate removal process and technology. Then I'm going to talk about 3 pilot studies that Veolia has done and its results. Then I'm going to end the presentation with a summary and conclusions. Then at the end, we can have some questions and discussion. Let's look at some sulfates limits in mining industry across the globe. Chile has the groundwater sulfates discharge limitation around 250 milligrams to 500 milligram per liter. On irrigation side, they have around 250 milligram per liter. Whereas US has a drinking water standard around 250 milligram per liter, and the industrial discharge standard is less than or around 500 milligram per liter. Currently, I'm working on a project where I'm going to give you the importance of sulfates. I'm working on a project where they have a toxicity limit, and we were finding to see what causing that toxicity, and we found it was a TDS, and the TDS contains mainly sodium and sulfate, and of which sulfates are very high in concentration. This is not related to mining industry, but I just want to get this example to see that what causing the sulfates has a toxicity issue also. So that's the reason we have very high standard limits on the global sulfates limits, discharge limitations. Let's look at the major sulfates removal technologies that are currently available. The first one is chemical precipitation process or desaturation process. This is mostly known as desaturation process, and it's a well-known process. Number 2 one is the barium salt precipitation or barium precipitation process. The third one is the biological treatment process. The next one is the ion exchange process, and the final one is the membrane or nanofiltration or reverse osmosis process. I'm going to go in detail of each this process. And the last one is the evaporation and crystallization process. I'm not going to talk much on that because evaporation and crystallization is expensive both on a capital wise and an operating wise. Let's start with the chemical precipitation process or desaturation process. Calcium plus sulfates reacts to form calcium sulfate. To get down to the sulfates to theoretical limits, theoretical solubility limits, that is around 1500 to 2000 milligram per liter, you need to have a good sludge recirculation and a one-time seed material to be added. What is a sludge recirculation? A portion of a sludge is recycled back from the clarifier or a solid liquid separator back to reaction tank. What does the sludge recirculation helps? Sludge recirculation helps to improve your settling characteristics, improve your crystal growth characteristics, reduce the chemical consumption, and also reduce the amount of sulfates in the effluent. And what does the seed material does? The seed material, as just when you add a seed material, it starts the reaction. So what mechanism that's happening in the chemical precipitation process is it's an actual chemical precipitation process plus absorption and co-precipitation of this calcium and sulfate onto calcium sulfate solids. And with good sludge recirculation, and you should able to do the chemical precipitation process within 30 minutes. Please note that temperature also plays an important role. If you have a low temperature water, your feed water temperature is low, then you may have to increase your reaction time, or else you have to increase your sludge recirculation rate to get down to low sulfates limits. That's around 1500 to 2000 with a chemical precipitation process. What's the advantage of this chemical precipitation process? You should able to get down the sulfates to theoretical limits. And if you have any metals, typically calcium is added as a lime is added as a source of calcium ion. So when you add a lime, what happens is if there is any metals, typically mine water contains heavy metals. So any metals that are present in the water will be removed as metal hydroxide. So you get calcium sulfate sludge as well as metal hydroxide sludge, and you'll have the effluent with low metal concentrations. So that water can be reused back in your treatment process. This is the most cost-effective process compared to other technologies, but the disadvantage of the chemical precipitation process is it produces a sludge that is a combination of calcium sulfate as well as metal hydroxide sludge. And also, if you have to meet lower sulfate limit, this chemical precipitation process alone cannot get down to low limits like around 500 or less than 1000 milligram per liter, depending upon your discharge limitations. So the next process is barium salt precipitation process. In the barium salt precipitation process, barium reacts with sulfates form barium sulfate. Most of you guys know that barium sulfate has very, very low solubility limit. It's less than 2 milligram per liter as barium sulfate. Now, when you have a barium salt precipitation, your effluent sulfates will be very low in concentration. But the disadvantage with the barium salt precipitation is it's very high expensive process and the chemical cost is high. And also barium is one of your TCLP metal. So the sludge can be sometimes a hazardous sludge. So for example, if you have two streams that contain barium and other stream contains sulfates, you can combine that and you can produce a barium salt, a barium sulfate sludge. But that way it's going to be inexpensive. But adding an external source of a barium, such as a barium chloride, is an expensive chemical. And also, please note that you are removing sulfates and you are adding chlorides. The equivalent weight of a sulfate is 48, whereas chlorides is 35.5. So means you're replacing every sulfate ion with 1.5 of chlorides or at least 2 chloride ions. So the disadvantage is you have high TDS and high expensive operating costs, but advantage is you should able to get down barium to very low, sulfates to very low concentrations. The next process is well-known process, biological treatment process. In biological treatment process, you have an anoxic condition where your sulfates are reduced to sulfides and eventually it's oxidized to sulfates. It's a two-step process. In first stage, what happens is your sulfate reducing bacteria, you add a food source like a carbon source, like a methanol or some kind of a carbon source. Then your sulfates present in the water and your sulfate reducing bacteria reduces that sulfate down to sulfides. When you have sulfides and your mine water contains heavy metals, most of the heavy metals get reduced as metal sulfides, and metal sulfides has very low solubility limits. And these sulfides eventually get oxidized to elemental sulfur. That way your sulfates are removed from the system. The next process is ion exchange process. Your feed has both calcium and sulfate. Your untreated feed goes to first to cation resin or cation ion exchange, where you remove cations, mainly the calcium. Then you send the effluent from the cation resin to anion resin or anion ion exchange, where you remove sulfates. This both cation is regenerated with sulfuric acid, anion is regenerated with lime, and you produce this regenerant waste which is high in sulfates as well as calcium, and you combine that and produce calcium sulfate sludge. This sludge is high in purity, and the effluent coming out of ion exchange process is very low in sulfates concentration. But the disadvantage is you need a lot of chemicals for regeneration, as well as you produce a lot of sludge. The next process is a membrane technology. The membrane technology mainly it's either nanofiltration or reverse osmosis. What is the difference between a nanofiltration and reverse osmosis is, in general term, nanofiltration is less tighter membrane compared to an RO process. What's the advantage of nanofiltration is it removes mostly the divalent, trivalent cations, anions, also oxyanions, but its advantage is it passes the sodium and chloride or monovalent cations. The advantage is you don't build up the TDS. And also the power required to operate in a nanofilter is lower compared to a reverse osmosis. Reverse osmosis rejects almost all cations and anions. And if wherever you have a reuse application, this nanofiltration is very good technologies to reduce sulfates to very low concentration, and your effluent quality is very good. But the disadvantage is the reject that produced in the nanofiltration is high in sulfates, and you need a sulfate treatment technology. And also, any membrane technology needs a good pre-treatment because there can be a potential for scalings like particulates. And number two, you have any heavy metals. Typically, mine water has heavy metals like aluminum, iron, manganese, molybdenum. All these are foulants to the nanofilters as well as for the reverse osmosis. Let's look at the two-stage sulfate treatment technology. The main advantage of this two-stage sulfate treatment technology is it produces sulfates to less than 250 milligram per liter, all the way down to 100 milligram per liter. The first stage is calcium sulfate precipitation process or chemical precipitation process or desaturation process, where you reduce sulfates down to 1500 milligram to 2000 milligram per liter, which is a theoretical solubility limit of calcium sulfate, sulfates. And the next stage is the advanced chemical precipitation process, where you reduce from 1500 milligram per liter down to 250 milligram per liter, all the way down to 100 milligram per liter. And the advantage of this process is you can reuse this water back in your treatment process. So let's look at the sulfates reaction, precipitation reaction. The first stage, calcium sulfate desaturation process, which I talked previously, is a calcium plus sulfate forms calcium sulfate. The second stage, or advanced precipitation process, forms an insoluble complex, which we call it as ettringite or calcium sulfoaluminate. The equation or the reaction is you add a lime, CaO, plus feed calcium, plus feed sulfates, plus a reagent. A source of aluminum is added as aluminum hydroxide, and water present in the reaction and forms calcium sulfoaluminate, CaO, Al2, Al2O3, CaSO4, and 31 moles of water. And this water, this calcium sulfoaluminate or ettringite, we add a acid to break down this molecule and regenerate the regeneration to regenerate the aluminum. Why we do that? Because we reproduce back the aluminum source or aluminum hydroxide and reuse in the ettringite precipitation process. The advantage of this one is the regeneration process is to reduce the chemicals or to reduce the addition of aluminum source. This slide shows you the ettringite molecule or calcium sulfoaluminate molecule. It's a very complex molecule with 31 moles of hydration. So I'm going to talk in next coming slides 3 pilot studies that we have done and to validate this two-stage sulfate precipitation process or technology. First pilot study was done in South America, in Chile. It's on a tiling pond water. The goal of this pilot study is to reduce the sulfates down to less than 250 milligram per liter so that they can reuse in their irrigation process. So that's the goal of the pilot study. And also we want to try to look at our two-stage sulfate process. The pond water has a characteristics you can see here around sulfates around 1830 milligram per liter, calcium around 690 milligram per liter. The feed itself contains mostly calcium and sulfate. The feed water has around 130% of calcium sulfate water. So feed itself had 130% of calcium sulfate water. And also in addition to that, the feed had molybdenum around 0.27, iron around 0.17, and there was manganese around 0.17 and iron around 0.04. Most of the cation and anions are imbalanced. So let's look at the concept. The pond water goes to the pre-treatment step. So since you have a nanofiltration, it goes through a pre-treatment step to remove iron, manganese, and molybdenum. And then after the reject goes to the first stage desaturation process to get down the sulfates to less than 1500 milligram per liter. And then after that, whether you can reuse back into the pond, as if you don't need to do an advanced process. If you want to reuse that water, you need to do an advanced sulfate precipitation process where you produce sulfates less than 250 milligram per liter, where you combine with that effluent with the enough permeate to reuse for your other process. This is a generalized concept, the same concept we used for our pilot study. So the pre-treatment include here was iron coagulation. The reason is molybdenum is an oxyanion and molybdenum should be removed with iron co-precipitation absorption process. The optimum pH for removal of molybdenum is around 6.5 pH, followed by multimedia filtration and green sand filtration, mainly to remove iron and manganese. Please note that both iron, manganese, and molybdenum are foulant for the nanofiltration. The SDI after our multimedia filtration or green sand filtration, after green sand filtration, was less than 3, and we used Dow NF membranes. One is 270 membrane and two of them are NF90 membranes. NF90 membrane is little tighter membrane. NF270 membrane is little less tighter membrane compared to the NF90. It has more permeability than NF90. So total we used 3 membranes in series. So let's look at the sulfate in the NF permeate as well as the concern and the rejection rate. So you can look here, the sulfate almost rejection was 98%. So NF is a very good application for the sulfate rejection. And the average sulfate we produced in our pilot study was almost less than 40 milligram per liter. The feed had around 1800, 2000 to 1800, and we were producing less than 40 milligram per liter of sulfates in the effluent. So the reject from the NF went through in a turbomix reactor. This is a Veolia proprietary reactor. The turbomix reactor is nothing but it's in a reactor that has a draft tube and a mixer. The advantage of the turbomix reactor is it has an axial flow that is very good for our good sludge recirculation. It also improves sludge crystal growth kinetics, and also it improves our sludge settling characteristics. The effluent from the reactor went to our solid liquid separator, which we call it as multi-flow, and a portion of sludge is recycled back to the turbomix reactor, and another portion is sent to the waste for the disposal. The feed had, after the NF, it was around 3200 sulfates and a calcium around 1000 milligram per liter. And the effluent after our first stage desaturation process produced sulfates less than 1500 to 2000 milligram per liter. So this slide shows the importance of sludge recirculation as a function of the calcium sulfate or sulfates removal. So what is a sludge recirculation ratio? It's the pound of calcium sulfate in the recycled sludge to the pound of calcium sulfate produced in fresh sludge. So for example, if I say 10 to 1 sludge recirculation ratio, that means 10 pound of calcium sulfate in the recycled sludge to 1 pound of calcium sulfate in the freshly produced sludge. So when I don't had any sludge recirculation, I was able to reduce sulfates from 3000 milligram down to 2000 milligram per liter. With 10 to 1 sludge recirculation, we were producing around 1200 milligram per liter of sulfates in the effluent. At 15 to 1, we had 1100, and 20 to 1, we had a little higher concentration. Mainly some of the sulfates came out of the solution. But I would say with a good sludge recirculation, you should be able to get sulfates down to less than 1500 milligram per liter. And also, please note, we ran our turbomix reactor around 30-minute reaction time. So in order to reduce further sulfates down to 100 milligram per liter, we need to go to advanced precipitation process, which is also called ettringite process. I already talked about what is a ettringite reaction and also the regeneration of the reagent. It's a lime plus calcium plus sulfate plus a reagent of aluminum, and with a water molecule forms this insoluble complex or ettringite or calcium sulfoaluminate. And this reagent or this ettringite solids, when you add acid to it, it breaks down the calcium sulfate and it reproduces the aluminum hydroxide or gibbsite. This gibbsite is reused back in the ettringite precipitation process. I'm going to talk about the concept. You can know more in detail. So here is the advanced precipitation process or ettringite process. the membrane reject, or the NF or oro reject. It goes to the turbomix reactor with a multi-flow. That's the first stage process where you reduce sulfates down to your theoretical solubility limits. Then it goes to the second stage process or advanced precipitation process. That's also turbomix reactor, where you add a source of calcium, typically lime or calcium chloride, whichever is available, and then a source of aluminum. Typically we add here is aluminum trichlorohexahydrate. We had a good results with aluminum trichlorohexahydrate. Then the sludge or the ettringite sludge or ettringite molecules or ettringite solids goes to the solid liquid separator. That's typically a multi-flow. Then the sludge, a portion of sludge is recycled back. You can see it goes back to the turbomix tank, and other portion is send it to aluminum hydroxide regeneration tank, which is nothing but in this slide you can call regeneration of the reagent. That's what we are doing in this aluminum hydroxide regeneration tank, where we add an acid. So what does this acid do? It breaks down the ettringite solids and it regenerates the gibbsite or aluminum hydroxide. So the gibbsite is produced in the sludge, or we can, as you can see, it's recycled back to the turbomix tank, and the effluent or the overflow from the aluminum hydroxide regeneration tank, it mainly contains calcium and sulfate. That calcium sulfate overflow high or rich in calcium and sulfate are sent back to the first stage desaturation process, where we remove that from the system as calcium sulfate sludge. And the regenerated gibbsite mostly is recycled back to the turbomix tank in ettringite, and you use that to reduce your sulfates down, and you reduce the amount of addition of fresh aluminum hydroxide. So this is a pilot study for the advanced precipitation process, and the pH is a very critical parameter, or I'm going to call it a very, very important parameter. When we ran, the typical pH for the ettringite formation is around 11.8. We ran at 11, it did not produce any sulfates. It did not, I'm not going to say it did not produce, it did not reduce the sulfates to lower concentration. At 11.5 pH, we were able to reduce sulfates down to 200 milligram per liter. At 11.8, we were able to reduce sulfates down to 100 milligram per liter. That's the very important parameter. The pH is a very important parameter. And also reaction time is also very important parameter. We typically ran the pilot around 60-minute reaction time. But with a good sludge recirculation, we should able to reduce that to 45 minutes reaction time. Please note temperature is also an important parameter. But increasing, it all depends on what is your effluent limitation. If you want to get down to 100, means you need to go all the way to 11.8, 12 pH. That means indirectly you're adding more and more chemicals. So it all depends upon to application basis. So here is the sulfate precipitation kinetics, or I'm going to say mainly for the reaction time. So within 15 minutes in our advanced precipitation process, we were able to reduce the sulfates from 1200 milligram per liter down to less than 100 milligram per liter. Even if you, I would say less than 200 milligram per liter, and if you want to go more and more, you see you need more reaction time to get to a very, very low concentration. So it all depends upon application to application basis. I would say typically with a good sludge recirculation with everything, you should able to get down to 100 milligram per liter, and your reaction time may be around 45 minutes to 1 hour. So in the regeneration process, we were able to, the ettringite solid had around 155 milligram per liter of aluminum as aluminum ion. with the regeneration process, we were able to recover almost 95% of our aluminum, and we were able to reuse in our system. That's we did in other pilot studies, and we were successfully able to do that. So the overall pilot or the process flow diagram is the feed water goes through pre-treatment step, mainly iron removal and manganese removal and molybdenum removal, followed by multimedia filtration, green sand filtration, and goes to NF. The recovery is around 50 to 60% recovery, and the sludge or the reject from NF went through two-stage sulfate precipitation process. After first stage, we were able to get down to 1200 milligram per liter. After second stage, we were able to get down to 200 to 100 milligram per liter. The effluent from the two stages, second stage plus NF permeate, we blended back and discharged to the effluent, and it has been discharged, and we were able to produce sulfates less than 40 milligram per liter. And the overall water recovery was almost or greater than 90%. The second pilot study, which was done in Greene County in Pennsylvania, this is on an acid mine drainage water, the effluent from a dense sludge process. The objective of this pilot study was to get down sulfates to less than 250 milligram per liter, also to validate our advanced precipitation process, the second stage precipitation process. The feed water had around 170 milligram per liter calcium, less than our first pilot study, and has sulfates close to our first pilot study, around 1800 milligram per liter, and TDS is also close to our first pilot study. The main goal of the pilot study is to validate our second stage sulfate reduction process and use the recovered gibbsite to precipitate our ettringite molecules or ettringite solids, and also to determine how much is the aluminum. Since we are using a fresh aluminum source, recovered aluminum source, we need to know how much is an aluminum in the effluent, also to analyze the surface characteristics of ettringite solids. So after our pilot study, the effluent sulfates were less than 200 milligram per liter. Please note this, we used a recovered or from our second stage regeneration process, the gibbsite. And we ran the pilot study for almost 2 months. And the effluent aluminum concentration is almost less than 0.5 milligram per liter. So sometimes we didn't even find non-detective. So for when we ran for almost 2 months, most of the time it was non-detective, but I should say maximum we found was around 0.5 milligram per liter. So that indicates most of the aluminum was bounded in these ettringite solids. So it was helping to remove the sulfates from the system. Here is a particle size distribution analysis, and we were found the ettringite solids were anywhere from 10 micron size to almost to 60 micron size. Most of the particles were around 30 micron size, but this was able to achieve mainly because of high or we had a very high sludge recirculation ratio. We were almost running 15 to 1 to 20 to 1 sludge recirculation ratio. That helped to improve our crystal growth or particle size. The XRD and scanning electron microscopy on the ettringite sludge showed us the major peak was ettringite, and a minor peak we found some calcium carbonate sludge and also some gypsum. So this indicated to us whatever sludge we produced or whatever solids we produced in ettringite reaction was only ettringite, not any other sludge. But there was a little bit calcium carbonate and a little bit calcium sulfate, but majority was ettringite. The next pilot study we done in South Africa, it's on a gold mine. It's also an AMD water or acid mine drainage water. The objective is here to get down the sulfates less than 500 milligram per liter. The feed had around 630 milligram per liter of calcium and sulfates were around 2600 milligram per liter. This was little higher than what we added in our first two pilot studies, and the TDS was around 3500 milligram per liter. So we ran the first stage desaturation process, we ran the second stage advanced etringite process and regeneration process. So the sulfates removal with your reused gibbsite or we recovered aluminum, we were able to reduce sulfates down to 500 milligram per liter. During the start of we ran this pilot for almost 3 months. During the early stages, we had high sulfates coming out, mainly because we had very low calcium to sulfate ratio and also to aluminum to sulfate ratio, which I'm going to talk in the next slide. But that because of low sulfates, low calcium to sulfate and as well as aluminum to sulfate ratio, we produced a high amount of sulfates in the effluent. As we were increasing the chemical dosage and also the recirculation ratio, we were able to reduce the sulfates less than 250 milligram per liter. As the pilot study was settling down, and we were able to get good effluent sulfates limits. So this slide shows your effluent sulfates to aluminum hydroxide to sulfate ratio. Aluminum hydroxide to sulfate ratio is a very important parameter that indicates how much aluminum need to be there in order to reduce your sulfates in the effluent. You can see that's what I said during our early stages of pilot, we had a very high sulfate. That's mainly because we were running our aluminum hydroxide to sulfates around 0.5 to 1 ratio. So when we started to increase our ratio, you can see that the sulfate started to get reduced in the effluent less than 500 milligram per liter. But the disadvantage is more the ratio, the more the chemicals you add, more the chemicals you add, more the operating cost you had. It's all case by case scenario. That's what I'm going to say. If you want to get down to 50, yes, we can get down to 50, but you need to have at least 3 to 1 ratio of aluminum hydroxide to sulfate ratio, and also similarly on calcium to sulfate also. So in conclusion or summary, NF, nanofiltration with a proper pretreatment should able to reduce your sulfates less than 250 milligram per liter. I would say less than 100 milligram per liter. Your NF should be able to reject almost all divalent, trivalent cations and anions, and you should be able to get sulfates down to less than 100 milligram per liter. And we saw in our pilot study, the rejection rate was almost or greater than 98%. The first stage desaturation process reduced our sulfates to 1500 to 2000 milligram per liter. Please note that you need to have a good seed material. When I say seed material, typically it's a one-time addition of calcium sulfate hemihydrate, which is a plaster of Paris, or you can add gypsum as a starting material to start the formation of calcium sulfate. And also please note you need to have a good sludge recirculation. 10 to 1, 15 to 1, 20 to 1 is a good starting point, and based on application to application you can increase or decrease the sludge recirculation ratio. And as I said, your seed material is added one time. If necessary, you can keep adding it, but I would suggest you to add only one time. And in this process, two-stage process, both chemical precipitation, also absorption and co-precipitation process happen in sulfates removal process. The etringite precipitation reduce the sulfates down to 100 to 250 milligram per liter. If you want to get down to very, very low concentration, you need to increase your reaction time. You have to increase your aluminum to sulfate ratio. Those are very important parameters. And also, we used a recovered gibbsite. Recovered gibbsite helped us to reduce our aluminum dosage or our chemical consumption or fresh aluminum addition. And the important parameters that are for the ettringite precipitation is pH. As I said, if you run at a pH 11, you will not able to reduce your sulfates less than 1000 milligram per liter. If you increase your pH to 11 and a half, you should able to reduce your pH around, sulfates around 500 milligrams to 200 milligrams. If you go all the way up to 11.8 to 12 pH, you should able to reduce your sulfates down to 100 milligram per liter. And another important critical parameter is reaction time. I would suggest, based on our pilot study, you can do anywhere from 30 to 60 minutes reaction time. Depends upon also, please note, temperature is also an important parameter. If you have a water temperature very low, then you need to increase your reaction time. Other important parameters in ettringite formation is calcium to sulfate ratio. Typically, 1 to 1 is good, 2 to 1 is also good, but it's on application to application. Also, aluminum to sulfate ratio is also an important process parameter. I would suggest the theoretical is around 0.5 to 1, but if you want to get reduce the sulfates down to less than 100 milligram per liter, I would suggest you start around 2 to 1 ratio. And the last important parameter is also sludge recirculation ratio. So with this, I conclude my presentation. Jill, I will hand over to you.
Great. Thank you very much, Shri, for that very informative presentation. Just a reminder, we did have some questions come in throughout the webinar, but just a quick reminder, if you do have any questions, feel free to ask those or type those over on the right-hand side of your screen under the questions panel. And with that, I will open it up for the Q&A session. Shri, one of the first questions that we've got here is, if we have both TDS and sulfate limits, does two-stage sulfate removal process reduce both sulfates and TDS?
That's a very good question, Jill. When you have a TDS limit and sulfates limit, you will not gonna reduce both TDS, because what's happening here in advanced or two-stage sulfate precipitation process is we are adding a source of aluminum, mainly aluminum trichlorohexahydrate. So we are replacing some of the sulfates with the chlorides. That means your TDS will not going to get reduced. You need to add additional and a small RO system in order to reduce your TDS. So what I would say to answer your question is, no, you cannot reduce TDS, but you should be able to reduce your sulfate. It's mainly for the sulfates removal process. In order to reduce TDS, you need to have an additional small RO system. I'm going to say a bypass RO system based on your TDS limit.
Great, thank you. Another question that came in is, what pH does the aluminum hydroxide regeneration tank operate at?
That's a very, very good question. Aluminum hydroxide solubility is low at a pH of 6.5 to 7. So when you add acid, we reduce the pH from all the way from 11.8 down to 6.5 to produce aluminum hydroxide. And that's the optimum pH, I would say, is 6.5 to 7.2.
Great, thank you. Another one, for gibbsite recovery, what acid is used and what reaction pH is needed to recover the aluminum hydroxide?
The acid we used is hydrochloric acid, okay? Please note, don't use, I would not say don't use, if you use sulfuric acid, means you are adding sulfates to the water, okay? You should know, I would try to say you add hydrochloric acid. Hydrochloric acid is used and you reduce the pH down to 6.5, and at that pH, the solubility of aluminum hydroxide is very low. You'll be able to precipitate all aluminum hydroxide back from ettringite solids. That's very good questions.
Another one that came in is, what is the optimum pH, reaction time, calcium sulfate, and aluminum sulfate ratio for ettringite?
Sorry, can you repeat one more time the question?
Sure. What is the optimum pH, reaction time, calcium sulfate ratio, and aluminum sulfate ratio for ettringite?
Okay. The optimum pH for ettringite is, as I said, it's around 11.8. That's where I want to operate. 11.8 is the optimum pH. The reaction time, it's based on application to application, some other factors. I would suggest with good sludge recirculation, you should run around 30 minutes to 60 minutes. I would suggest to run a pilot study or a bench scale study to optimum to determine based on the case scenario. I would suggest around 30 minutes to 60-minute reaction time. Then calcium to sulfate ratio, typically I would start around 1.5 to 1 or 2 to 1 ratio, and aluminum to sulfate ratio. It all depends what is your effluent goals. If you're trying to reduce down to 100 milligram per liter or 50 milligram per liter, I would suggest a higher dosage of aluminum to sulfate, around 3 to 1. If you want around 500 milligram per liter of sulfates, do 2 to 1 or 1.5 to 1 ratio.
Great, thanks. We've got time for a few more questions here as well. Another one that came in is there any fouling issue with ettringite precipitation in the clarifier / reactor or piping?
Are you talking about any plugging issues? Is it a plugging?
Yes.
We did not had any plugging issues based on our pilot study. That's what I can say. But if you say, since this ettringite molecule has 31 moles of hydration, but if you try to concentrate up, eventually if you don't remove from your clarifier, then eventually it's going to get plugged up. That's what I'm going to say. So you have to have a continuous removal system, or you have to have a wasting system.
Okay, great. Thank you, Shri. Another one is, let's see, has Veolia considered thermal technologies for mine water treatment?
For thermal technologies, can you be more specific? Just what kind of thermal technologies? That's I don't know. We didn't looked into any thermal technologies.
Okay.
I would say we not looked any thermal technologies. That's what I can say. I need to be more specific. What kind of thermal technologies are they looking at? You need to give me an example.
Yes. Evaporation is what it looks like.
Oh, evaporation and the crystallization process. No, we did not look because it's a little high in capital cost and operating cost, and we did not look at that in any of our studies.
Okay. See, another question that's come in here is, can the ettringite, I apologize, I'm bad at saying this word, but can the ettringite be dewatered to form a solid that can be disposed of in a landfill or in the tailing storage facility?
Yes, you can dispose of. It is a non-hazardous. You can dispose of in a landfill and or else in your tailing pond. I would say it's better to send it to a landfill rather than sending back again to the tailing ponds. What happens is if you send it back, If it will never, the sulfates will never gonna break down. But if your tailing pond has acidic in nature, then automatically then that starts to break down the astringent molecule, and then the sulfates are released. So I would say send it to landfill, yeah, until your tailing pond does not have low in pH. Okay.
Okay. Another one here is, what is the effluent aluminum concentration?
It is around, I would say most of the time we got non-detect, but the higher range we found is couple of times we were around 0.5 milligram per liter as dissolved alumina.
Okay. We've got time for just a few more questions here, but one that just came in is, what percentage solids do you get with dewatering of the sludge?
We got around, means in the pilot study, we were able to get down to 20 to 30% cake. The astringent solids, okay? On calcium sulfate, you can go up to 40 to 50% easily.
Great. Thanks, Sri. I'm trying to see if we've got any other questions that are here. Let me see real quick. Just wanted to make one quick comment or additional follow-up comment on Shree's comment on the thermal technologies for evaporation and crystallization. Is we do have technologies available in the evaporation and crystallization technology systems. And then if anybody is interested in that, we can definitely follow up one-on-one afterwards with more information on specific thermal technologies. And that appears that we've got all the questions. I apologize if I have missed one, that we will follow up with you personally after the webinar. And with that, we will go ahead and conclude today's webinar. And we do thank you for your time today. And this has been recorded, and we will send this out to you so you have that, I believe, tomorrow. So thank you very much.
Thank you.